Simple machines. There are 6 different simple machines. The first one that we'll talk about is the wheel and axle. Okay, you've seen these before in cars and bikes. Okay, you've got the big wheel and then you've got an axle coming out of it. Okay, and they both spin around. Okay, then we also have a wedge. Okay, and you've seen these before in everyday life. An axe would be a wedge. Okay, a knife would be a wedge, a sword would be a wedge, a doorstop would be a wedge. Okay, so all of these are shaped kind of angled in, at least on one side. Okay, and wedges are used to split things and to redirect force. A lever, okay, a lever is something that pivots around a fulcrum. So a wheelbarrow would be an example because it pivots around the wheel. Okay, you lift it up, it pivots around the wheel. A car jack would be another example. A seesaw would be another example. Okay, it needs to pivot around a fulcrum. The next one up is a pulley. Okay, a pulley is a rope or string, okay, something that winds around a wheel. Some examples might be your blinds, okay, they might be set up, they wind up, the string winds up around a wheel, okay. Then you've got an inclined plane. Basically this is a ramp, okay. It's something that is angled and it's stationary, and then we move things up and down it. Okay, the roads are kind of angled. Sometimes you see the road kind of goes up in the middle. It's not that exaggerated, but that's what the water drains off to the side. Okay, that's an example of an inclined plane. Okay, the next one we have up here is a screw. This is an inclined plane that is wrapped around a post. Okay, so you take this inclined plane and you wrap it around. Okay, some examples, not to use it in the definition in your example, but a screw that you work with in woodworking is an example. Bolts, okay, are examples. The caps to your water bottle lids. Are an example, okay? It's kind of just a threaded idea there, okay? So these 6 simple machines make up more complex machines. You put some of them together, you can get a complex machine, all right? So let's look at a simple machine. Something that is a misconception is that a lot of people believe that simple machines can increase the amount of work that's done. That's not true, okay? You cannot increase the amount of work done. If there's no friction, you get the same amount of work out. However, there's typically friction, so you're usually doing more work, okay, to put in than what you're getting out, all right? So if that's the case, why do we bother having these? Well, remember, work is force times distance. So even though we do something a little bit more, it might be helpful to us. How? Okay, well, you can change the direction, okay? Pulleys and levers change the direction of a force. So let's say there's a barn and you're trying to lift barrels of hay up to the next level, okay? To stand up here and then try to pull the barrel up is going to be quite difficult, okay? Whereas if you hook up a pulley system up high, attach it, you can then pull on the rope from down here and lift the barrel up, or the stack of hay up, okay? Makes things a little bit easier for you because it's a little easier to pull down. Plus you're not up here trying to pull up. You're less likely to fall off, so it's a little safer for you, okay? What else? Why else would we use this? Well, you can increase the force. You can't increase work, but you could increase the force. Remember, work is force times distance. We're just going to ignore the whole angle part for right now. So I could increase the force. okay, I might not get as much work out, but if I move things a big distance on one end, okay, I can increase the amount of force. So when do we use this? If you want to lift a heavier load, so for example, your car jack, okay, you've got the little car jack, okay, and you're going to lift that up and down and up and down and up and down. You've got your car over here, which is pretty big, okay, and it's heavy. I can't lift this car up by just going over there and pulling up, okay? But if I hook up the jack, okay, and go up and down lots, okay, I might move this up a couple inches, which is what I need to do. So I put a big distance in, which means I'm doing a lot of work because I'm multiplying by a big distance, okay? And therefore, on the other side, I'm getting a lot of force out with a little distance. It doesn't move as far, okay? Similarly, maybe you don't need a big force. Maybe you need something to move really far, okay? Like a catapult, okay? So you've got your stuff here, and it starts down, okay? So it started down here, and then it flew up. This started up here, and somebody pushed down with a really big force, okay? Now this is smaller, so this is a smaller force, it's the gravitational force on a small object, okay? But it's gonna go really far, okay? So maybe you need to increase your distance. So you can't do more work, but you can get a bigger force out if you use a big input distance, and you can get a big distance out if you use a greater input force. Okay, there's always a little bit of a trade-off there. All right, one of the things we often talk about with simple machines is efficiency. How efficient is our simple machine? Well, efficiency is the percent of work you get out compared to the work that you put in, okay? So you take the amount of work that you get out and divide by the work that you get in, they put in, all right? So you can never have more coming out, so you can't be more than 100% efficient, all right? But if there's no friction, then efficiency can equal 100%. Unfortunately, there's quite often friction, okay? And in that case, your efficiency will be less than 100%. So let's give you an example here. Let's say if the efficiency is equal to 70%, what does that mean? That means if you put 100 joules of work into something, you get 70 joules worth of work out. Okay, so you do 100 joules worth of work, some force and some distance, you're going to get 70 joules of work out if you are 70% efficient. So that's how this works. Okay. Another thing we talk about is mechanical advantage. So what is mechanical advantage? Well, let's go back to the car and the jack example. Let's say that the car is 2,000 pounds. I can't lift that, okay? But with my lift, with my car jack, I can go ahead and apply 100 pounds worth of force, because I can push down and apply 100 pounds, I think, okay? So what does that mean? If it's going to move up a little bit, that means that I'm doing 20 times more work. My mechanical advantage is equal to 20, okay? I'm getting 20 times the force out that I put in, okay? Now, your ideal mechanical advantage, okay? Whenever there's no friction, this is the maximum mechanical advantage that you could possibly get. And what you do is you take your distance that you put in and divide by the distance that you get out. This is the upper limit, okay? You can't get better than what this would be, all right? And it again is it's your ideal mechanical advantage without friction. And then your actual mechanical advantage, you take the force that you get out and divide by the force that you put in.